The NSM course on GPU programming with OpenACC. In the last two lectures, we looked at introduction to GPUs and basic OpenACC Hello World program, which was just to make sure that we get started with OpenACC installation and compilation. Today, we are going to look at, and in the next 4 lectures, we are going to look at specific constructs which are going to be very useful from the perspective of parallelization on GPU. Today's topic is going to be a compute construct called parallel. We did look at parallel in our previous discussion. However, we are going to look at it a little more closely today. So let's get started. Yeah, and as before, feel free to ask questions anytime. Okay, so the basic small snippet of code that I'm showing here, which will be part of a larger main program, will be hash pragma ACC parallel. After that, I'm giving an opening brace on the next line. Then there is a printf and closing brace on the next line. So what this makes sure is that the hash pragma ACC parallel gets applied to the whole block that is enclosed in these braces, right? So which means that you can apply that parallelization to everything that is inside this this block of code. So this block of code is just a scope in the context of C, and if you do not specify these braces, then the first line which is going to be occurring just after hash pragma ACC parallel, that line is going to be being applied this particular parallelization. Okay, so as a good programming practice, even if you have a single statement, it's a good practice to put it into braces so that we avoid the sudden surprises. I mean, because of indentation, you might, I mean, if you don't have these braces and you put lots of different codes indented, and you feel that all of those are going to get parallelized, that is not going to happen. Right? This is similar to what happens when you have if statement followed by one instruction or multiple instructions. You need to give braces. It's a good programming practice to give braces to avoid any surprises. So that's what is going applicable here. This simple piece of code, you can actually have resemblance with respect to what happens in OpenMP. Those of you who are aware of OpenMP, the pragma is, would look like hash pragma OMP parallel, right? Instead of ACC, we just have OMP, and then I give this block and this printf, how many times am I printed? Can somebody tell me, in case of OpenMP, what is the output that you expect? Himanshu says prints many times. Okay, anybody else? Okay, so that is correct. In fact, what Himanshu is suggesting is that this particular printf, just by making it parallel, can get printed multiple number of times. Srinivas says prints the number of threads given, but I haven't specified any number of threads anywhere in the program. What does the output give? Actually, let's discuss that. How many times will this get printed? Srinivasa stated maybe it prints it number of threads times, but in my OpenMP program, if I have not specified any number of threads, what will happen? I know the discussion should be on OpenACC, but hopefully it will make it clear, at least distinguish between the outputs. Himanshu says depending upon the number of cores available, yes, that is what exactly happens in the context of OpenMP. By default, it finds out the number of cores available and creates those many threads, and all the threads, in case of OpenMP, all the threads on the CPU are going to execute this block of code, and therefore how many times am I printed might get printed 4 times, 8 times, 32 times, depending upon the number of cores you have in your machine. So that is correct that it prints multiple number of times. What happens when we execute this in case of OpenACC. The reason why I'm coming from OpenMP is because some of you might actually, when you are trying things in GPU, there is a good chance that you will have the output turns out to be, when I compile it and run it, the output turns out to be a single line. How many times am I printing? Does that mean that it actually got parallelized or not? Whether it ran sequentially, one, and if it ran sequentially, where did it run? Did it run on CPU or GPU? Right? Because we said that that -acc command line parameter was missing yesterday, and then the code was running directly on the CPU. Right? So is the same thing happening? Assuming that I have taken care of all those issues, the output of this code is obtained from the GPU, from the accelerator, and it is actually running with a single thread on the GPU. That means it is running sequentially on the GPU. This is typically the default of the OpenACC acceleration. You can change this default by making certain changes to OpenACC variables or the configuration on your machine. But this is usually the default with the NVIDIA HPC toolkit. When you install and run it, you will be able to get a single output. Right? So let's understand this parallelization block. Whatever be the set of statements inside this parallelization block, all those statements will get executed by typically multiple threads. In this case, since I have not specified anything, it is just one thread. Okay. So yeah, so I'll just explain that. This particular parallelization construct usually creates a gang of workers, right? So one or more gangs of workers are created. This is dependent on your configuration. Typically it is one, at least on my machine, and most other students find that it is going to be one gang which is going to get created with a single thread, and therefore it runs sequentially. Like the three levels of the compute hierarchy we saw yesterday, the gang, then the workers, and the vectors, all of these remain fixed during this parallel region. The braces specify the parallel region, and the number of threads with which you are running these does not change during this time. Okay, so in a sense, you should view this parallel block as a kernel or a function which is going to run directly on the GPU with certain kernel configuration in terms of how many threads with which I am running the kernel. Okay, so let's see. Okay, there are no questions. Yeah, and each gang executes the parallel region. You can view that each thread actually executes the parallel region. In this case, there is a single gang, single thread. Note that gang is a collection of threads, but gang's configuration can change, and we will now specify how to change, how to make things more interesting by running it in parallel. Okay, so I'm going to specify that with a clause which says num_gangs and in parenthesis some number, and that will help me parallelize this with two threads, essentially two gangs each containing one thread, and then I see the output. Which gang has printed which output, we don't know. There is gang number 0 and gang number 1, and they can print the output in any order. It's just that we know that now there is some parallelization happening on the GPU because of this num gangs of 2. All right, so let's do some classwork. I'm going to give you this piece of code or small snippet of code. Assume that the other things are taken care of. There is main, etc. All that is there. And now there are two blocks of code. First block says printf hello and printf bye, and that is invoked with 10 gangs. After that, there is a printf host, and then followed by another pragma parallel with number of gangs equal to 3, which prints 1 and 2. I want you to think about what will be the output of this particular snippet of code when you compile and run your OpenACC program. So please think for a few seconds. And those of you who have some answers, whether correct or wrong, doesn't matter. If you want to discuss, please feel free to paste in the chat box or unmute yourself and see. And in the process, if there are any questions, feel free to ask. Okay, Rajanya says the first thing that will get printed is hello. I hope that is what you. Genesis cannot get a new line in chat box. Yeah, sure, no problem. That's fine. That's fine. You can just separate it by spaces. I'll be able to figure out what the output is. No issues. Okay. Are there others who want to think about or at least share the output? Whether you share your thinking or not, you should definitely think about it. Right? Okay. Swapnil says hello and by 10 times, different or same order, followed by host, followed by 1 and 2, 3 times, different or same order. Pranav Diani says prints hello and by 10 times, different orders, host, and then 1 and 2, 3 times. Himanshu says anyone is facing problem with the video. I'm hearing broken audio every now and then. Okay, my apologies if the network is bad today. Rajanya says hello, bye bye, hello, hello, by 10 times, followed by host, zeros, and then host, and then 1, 2. I see. Josh is also facing the issue. I'm sorry. I think my network might be causing some trouble today. I hope the recording happens correctly. All right. So, yeah, no, maybe temporarily it goes bad. I don't know what has happened to my network. Okay. So let's hello and bye in random order. Okay. Pranshu says that. Sure. So I think many of you have suggested something similar, that hello and bye are going to get printed in uh, 10 times, followed by host, and then 1 and 2 are going to get printed 3 times, right? There are some questions which can happen. So essentially, the output is going to get divided into these 3 parts. First for the first pragma, then the second for the host, and the third one for the second pragma, right? Let's analyze these. And okay, within a particular block, for example, let's say the first pragma, is it possible that hellos and byes might get jumbled, right? And some of you say that yes, it will get jumbled because this is running in parallel, and therefore you might find those in some random order. Okay, one question I have there is that can the first output line be by? Can the first output line of this whole program be by rather than hello? Okay, Swapnil says it's possible. Panshu also agrees. Pranav also says yes. And he actually says something more, that it can be actually 1 or 2 also. Nitin says yes, it can be, as it's parallel processing and randomness of thread is always possible. Sure. Is there anybody who wants to say no? It's not possible. Okay, Rama says no. Okay.
Yeah, because obviously, I mean, looks before by hello has to be printed essentially.
Okay. Okay. Sure. Anybody else wants to agree with one of the two parties? Yes and no parties. Himanshu says, how are we sure that the 3 parts are executed sequentially? Very good. Yeah, currently we have not discussed that, but yes, that's a valid question, and let's try to answer that as we go along. Okay. Okay, nobody else wants to agree with Rama. Swapnil says, if these are queued and taken up for processing, then it will be hello first. Okay. Just says not possible as the instructions are processed in order. Ajanyas also thinks that it is no. Durvajyoti says, I had a slightly different question here, which is related to the execution model of OpenACC. This printf, which is a standard library function from stdio, so either this printf has to be translated to a GPU code or printf has to be a device-specific implementation. Yes, I'll come to that, Durvajyoti. It's a very valid question, and it will actually reveal some of the execution semantics as you have rightly thought about. Okay, so let's come back to this. Let's think about the first block, which is run by 10 threads. Okay, each thread is going to execute this particular block of code, piece of code in parallel. What does that mean? That one thread, let's say thread 0 or gang 0, is going to execute this block of code in the same order. And therefore, first thread or 0th thread is going to print hello and bye. Okay. Think about, let's say, gang number 5, which is probably going to get executed in some order. That will also print hello and bye. Now, what about the outputs of thread 0 and thread 5, or gang 0 and gang 5? These outputs can get intermixed at any point in time, right? However, as far as one thread is concerned, any one gang, if you think about any one thread, that is going to execute this piece of code sequentially. That is guaranteed. It can't parallelize this. If there are 10 statements inside this block, or let's say 100 statements inside this block, that doesn't mean that the 100 statements are jumbled up. It just means that these 100 statements are executed sequentially by each thread, but these multiple threads can execute these 100 instructions in parallel. And therefore, there could be arbitrary interleaving of these 100 instructions possible across threads. As far as one thread is concerned, it is always going to happen in a particular order, which is given by the program order. Therefore, in this case, you will, irrespective of how the interleaving is, the first string that gets printed cannot be anything other than hello. I mean, bye cannot be the first string that gets printed. Okay, so it's not the parallelization of hello and bye, it's the parallelization of this whole block repeated 10 times. And one block is always sequential. Okay, this should be clearly understood. So the semantics of the sequential execution of this block on the CPU side are maintained on the GPU side also. It's just that this gets repeated by different threads in parallel, and therefore hellos and byes will get printed in arbitrary orders, but the first string has to be hello, the last string has to be bye in this particular block of 10 gangs. Is this clear? Any issues, any concerns about this one? As far as queues are concerned, we will come to the queues part, but the queues are not associated with a single parallel block. Queues are associated with multiple parallel blocks, and as Himanshu was asking, that how are we sure that these three parts are going to get executed sequentially? If there is something more to it which we have to understand, one of that parts is that if you have these two pragmas concatenated, I mean in some sense concatenated because there is printf host in between. So first pragma is concatenated with the printf host, and the printf host is concatenated with the second pragma. So these two pragmas are not going to get executed in parallel. These are always going to get executed one after the other because they are by default going to the same command queue by the same stream, and therefore you will always see that all hellos and all byes are printed completely before any of the one or two get printed by the second pragma. Okay. We have still not said anything about the printf host, but it should be clear that if you have these multiple pragmas coming one after the other in your OpenACC program, then these pragmas are going to get fully executed before you reach the other pragma, right? Because there is a command queue and that command queue is sequential. Does that seem reasonable, Himanshu? At least part of your answer, part of your concern is should be addressed by this. The second part that is required here is that what happens to this printf host? Right? Is there a guarantee that, I mean, who is executing this printf host, by the way? Is it CPU or GPU? Any suggestions? Okay, so Uro says CPU. Rajanya also says CPU. Okay, so yes, it gets printed by the CPU, and that's why it is printing host there. But the reason why that happens is because there is no pragma which is enclosing that print. The scope of the first pragma ends with the closing brace, first closing brace, and the scope of the second pragma starts with the opening brace, the second opening brace. And therefore, that printf host is not part of any of the accelerator directives, and therefore it has to be printed or executed directly from the CPU, right? The way we write the usual other instructions if there were no pragmas and so on. Okay, so therefore that printf host happens on the CPU. Now the question is, what happens with respect, now this first pragma is being executed on the GPU, the printf host is happening on the CPU, and the second pragma is again happening on the GPU after the first pragma is over. This part is clear, but still this doesn't say that these three parts are being executed one after the other. You are right, and that requires us to have additional information about the pragma parallel, that after the pragma parallel, by default, there is going to be a barrier. After hash pragma ACC parallel, by default, there will be a barrier which will block the CPU, which means that the CPU is going to wait for all these hellos and byes to get printed, all the processing to happen within those first block of this pragma, and only after that CPU is going to go ahead and print host. Okay. If that is the case, then we can imagine that hellos and byes will get printed in some order, hello being the first one, by being the last one in that output. After that, only after 20 lines of hello byes are printed, we are going to see host. Only after that, CPU is going to start executing the next part, which is going to launch another kernel, another function on the same GPU, which will then start printing 1 and 2 in parallel. And there will be 6 such lines printed in some jumbled order. It's just that 1 will always be the first and 2 will always be the last line in this output. I hope this part is clear. If there are any questions, feel free to ask. I'll just take up some of the questions which I have not taken so far. Yeah, so as far as Dhruva-Jyoti's concern is related, for example, there are certain functions which are available. So, okay, let me make it clear that we have these two devices, CPU and GPU. If you want to run some code on the CPU, that code should be available on the CPU and possible to be executed on the CPU. The GPU is a different architecture altogether. So it's not possible that you take the CPU code, push it to the GPU and start executing and it will run. That doesn't happen, right? Like you cannot run a binary which is compiled for one architecture and just run it on another architecture and it will run. It will not run. In a similar manner, CPU and GPU are two different architectures, and therefore you cannot really run the same function on the CPU, which is running on the CPU on the GPU, or vice versa. So what we need to do, and what the PGI compiler is going to do, is that there are some libraries, some library functions which are already implemented for the GPU. One of them is printf. So printf is given more like a, let's say, utility function, or let's say some debugging help, and printf is actually also implemented as part of the GPU library. The implementation is going to be similar to what happens on the CPU, but it needs to be separately compiled and run on the GPU. So this printf is available. But what about some function which might be part of this pragma parallel or somewhere else? We will see more such examples coming later. If that function is not available on the GPU, what will happen?
Yeah. So I was exactly thinking of that. Let's say if it is not printf and I have something like an add 1 plus 2.
Correct.
So what will happen in that case?
Yes. So there are two ways in which that gets addressed. One is that depending upon your compiler and runtime, you will get a runtime compile time error. That this particular function is not available onto the device, onto the accelerator, and therefore, because while compiling, you need to link it with an appropriate library which should have the implementation of that function. If it is not there as part of the GPU library, you will get a compile time error. The second way in which some of the compilers and runtime might allow you to do this is, which doesn't happen, at least to the extent I know, but it can happen, is that except for that particular line, everything runs on the GPU. You get the result back to the CPU, whatever is required. You run that particular function on the CPU and then again go back and run it on the GPU. Right? So this is possible to be implemented, but and I'll show you at some place this is going to happen, but this is not going to happen inside our parallel block, because a kernel gets created for the whole block, right? A device function gets created for the whole block, and therefore you won't be able to run something which is not available on the GPU. Okay? So yeah, I hope that clarifies, Dhruv.
Yeah, but that means in this case, that's a big drawback, right? So if I can't call my some function which I want to write separately inside a parallel place, is it?
Okay, so if there is a parallel, if there is a function which you want to write, which you want to call from the GPU, that is perfectly fine as long as that code you are able to compile for the GPU. For example, if I just call some function fun here, right?
Yeah.
Right, so if that function contains usual numeric computation, all of that is possible to be done on the GPU, then the compiler is going to generate GPU code corresponding to that. In fact, the compiler, in many cases, depending on and subject to certain optimizations, will generate two codes corresponding to the same function. One for the CPU, another for the GPU, right? Assuming that you are calling it from the parallel block or other.
Yeah.
Right. So it will, you will be able to call arbitrary functions from here as long as you have the implementation. There is no problem.
Okay. So then the question comes in that, let's say I have a third-party library. Say I'm using some Boost library, right? C++ has some Boost libraries. So those will probably not work, right?
Yes. In fact, many of the simple C libraries like even string copy, string length, etc., these are not implemented on the GPU, and therefore we won't be able to call those from these parallel regions.
Okay. Yeah. Okay.
Yeah.
Thank you.
Good. Yeah, that was a good observation, and this is going to hit us badly at some point in time, maybe a couple of lectures from now. Yeah, so I'll come back to the questions then. Because queues are processed sequentially, but from multi-threading perspective, it will be random. See, yes, so queues are processed sequentially. A queue contains a complete command. That command is essentially, each command you can view it as one kernel execution or one block of code execution. That block of execution is going to be parallel. But two such blocks, that is two such commands or two elements from this queue are going to be processed sequentially, and therefore the kernels will execute one after the other. Himanshu says, what exactly was done by CPU and what was done by GPU here? The GPU does hello by, CPU does host, GPU does 1, 2. Yashpal says, what if there was no host? Okay, good question. If there is no host, still there is a barrier after the parallel block. So anyway, the CPU is not going to start executing the next pragma. Even if there is a possibility, and just 2 slides from now, we'll be able to remove that barrier, right? And if that happens, still the second pragma is going to invoke a kernel which is going to go into the same command queue, and therefore hello bys and 1, 2 are always going to be fully separated. There won't be any 1 or 2 coming in between the hellos and bys. Right? So the two outputs, the two kernels are going to be fully separated, even if there is no barrier in between, because the barrier means something between CPU and GPU. As far as the two GPU kernels are concerned, the first block and the second block, those are anyway going to get executed sequentially. What will happen if a counter is put like I++ in a loop? Okay, that's a good question. That is going to require us to talk about synchronization, because if that variable is going to be shared across all threads, then that I++ is going to involve some sort of a data race, right? So you are reading the value of I as well as writing to it, and if that I is shared, then that is going to be causing problem, because multiple threads are reading the value of I and writing to the value of I, and therefore the final output may not be, let's say I++ is there in the first block, we expect that, and initially let's say I equal to 0, we expect that the output, I mean the value of I at the end of the block should be 10, but it might not be, it might be smaller than 10. It won't be larger than 10 in most architectures. I mean, there is a little bit of technicality there, that there are some architectures which support concurrent reads, concurrent writes, ARCW, etc. But yeah, ignore that for now. For now, it will be the case that the value might turn out to be less than equal to 10 at the end of that parallel block, and we'll study that a little bit in a while. Okay, just says even if there is not printf host, then also there will be barrier after each clause. Yes, that is correct. Loop can be parallelized using different construct that will by default take care of I++. There will not be any data races in that case for I++. Yes.
Okay. I was talking about different constructs. So
yeah, I understand.
Loop construct by default take care of I++, right? So they don't, I mean, there won't be data race for that, right?
That is correct. So what Josh is talking about is, let's say you have a for loop for I equal to, like we had yesterday, hash pragma is ACC parallel for, a parallel loop. And then you have a for loop there or a while loop there, which is involving that I++. That will be privatized, that each I is going to go to each thread separately. And therefore, or a block of I's or a chunk of I will go to each thread. And that will be taken care of by the OpenACC library, that different I's are privatized and therefore they will not interfere with each other. But I think the question that came up from Rajanya was, if there is I++ and I is a shared variable, then what happens? And we will soon come to it. There will be data race by default in such cases if it's a shared variable, and we have to be careful. Careful meaning we'll have to introduce some synchronization which forbids such thing from happening. in the sense that I always want I to match the sequential execution. In the sequential execution, the value of I at the end of the block is going to be 10 because I plus plus is happening 10 times. So I want the parallel execution to also follow that. So that will require me some sort of a synchronization, where we can use some sort of an atomic instruction to make sure that I plus plus happens. Okay.
Continuing to the one of the earlier discussion,
Yeah.
The functions, right? In CUDA, we have these device functions, global functions, and host functions. So
Correct.
here also, do we have something like that, or people don't recommend these kind of functions here?
Yeah, so we don't have that distinction here.
Right.
However, any function that you define that can be used anywhere, either on the CPU or the GPU by default. So in a sense, by default, these are host device functions.
Right.
That is, yeah. So that is what is the default that we can expect. But yes, as I said, there are some restrictions depending upon which functions we use, and let's say some library function is unavailable, etc. So that is going to come.
Right.
Like,
so user-defined functions typically we can use.
Yes, you can use arbitrarily. Correct.
Sure. Thank you.
Yeah. Okay. Shri is asking how to assign execution of a particular block on a specific core or CPU or GPU. A particular block, we can have certain constructs which allow you to have execution of a particular block being done, or let's say that I have 10 gangs, and out of which only if my gang ID is 0 to 4, then do something. Otherwise, if it is 5 to 9, then do something else. Such a processing you will be able to do. There is an if construct which is provided for this purpose. However, mapping of this to a particular core is not in our hands, right? So, can a particular thread run on a particular core? No, we can't. We don't have any control of that. Right? Whether it is running on the CPU or GPU, that we can do, right? You just remove the pragma and it will run on the CPU. You add the pragma, by default it is going to run on the GPU. Is it possible that part of this parallel block is running on the CPU and part of it on the GPU? That is also possible, although I am not aware of the details, but there is this heterogeneous CPU-GPU processing possible, but I am not aware exactly how that gets done. So yeah, I won't be able to comment on that. But in general, you can always push some things. For example, I'm printing host here. That part is running on the CPU, right? So that I can parallelize, let's say, with OpenMP. And I have this accelerator part, which I'm processing with an accelerator. And both of these can run together, right? Although currently there is a barrier, we'll remove it. And then we'll be able to run these codes on CPU and GPU anyway. We'll come to that soon.
Sir, I had another question, like continuing from Sri's question, like how to assign an execution of a particular block. My thing would be, in case of the GPU, as we said, you have different cores. All those cores have uniform access to the memory, is it? And it's not like...
Yeah, as far as the RAM is concerned, yes.
Okay.
So I'll also mention something additional. In the context of CUDA, there is a notion of a memory hierarchy. There is a global memory, but then there is also something called as a small shared memory or scratchpad memory, which is available for each block of threads. So typical size of a block is 1024, as we saw in that computation hierarchy. So all these threads inside the block can share data very fast with each other via this shared memory. Such a notion is not available in the context of OpenACC. So therefore, they will always go for the global memory. As part of some optimization, the implementation might make use of shared memory. That is okay. But to the programmer, this is all not visible.
Okay.
Yeah, CUDA will have better control, but yeah, not at this, because that is quite NVIDIA specific, that L1 cache being shared by all the threads within a block is quite NVIDIA specific.
Yeah, okay.
Yeah, sure. Yashpal says, is there a possibility of nested pragma? Good question. There is a possibility of nested pragma. However, that is currently compiler dependent. So as far as the compiler that I have tried, it doesn't allow the nested pragmas to be present. Although on GPU, the GPU that I tried on, that does support nested kernel execution. So the CUDA code can run nested kernels, but OpenACC did not support the nested pragma. So, however, maybe either you should check that in your compiler whether that supports nested pragma or not. Like even the hash pragma ACC parallel by default should run with one thread, but then that is also configuration dependent, and therefore if your configuration allows something else, maybe it will run with a here. Okay, some discussion. Die cannot precede hello for the same thread, but die can precede hello in general across threads because the hellos and byes might get intermixed. Can host precede the first hello? It cannot because of this barrier. Right? So host will always get printed after the last by. Can die follow the last two? That is 1 and 2 get printed, and after that by gets printed. Is it possible? That is also not possible because the first kernel gets fully done before the second kernel is taken for execution, and therefore hello and by cannot intermix with 1 and 2. Okay, any questions so far on this output? Otherwise, I might ask you to do some classwork a couple of slides from now. All right. So let's understand a little bit about barrier. Right? A barrier is a synchronization point. What that means is that all the threads, if there is a barrier instruction, all the threads need to come to that instruction, and all the threads need to wait before any thread moves ahead. Right? And only after all the threads have reached that particular instruction, that particular barrier, that particular point in the program, only then the next instruction is going to get executed by any of the threads, right? So think about it this way, that let's say all of us are in different cities, right? And we decide to go to, let's say, Kashmir. What we all decide is that let's all meet in Delhi, and from there we all will go together to Kashmir. Okay. So when, let's say, different people are coming to Delhi, they are going to reach there at different times, but nobody is going to take the next route to Kashmir until everybody has reached Delhi, right? So therefore, Delhi acts as a barrier, or coming to Delhi acts as a barrier. Right? In a similar manner, all the threads are going to finish their execution, meet at the barrier at different times, and then when all the threads have come there, then only the next instruction happens. Yashpal is asking, is there any way to remove the barrier? I know that we don't like barriers. Yes, OpenACC does support removal of a barrier using the async command. So async clause can be given to parallel, which will remove that barrier, and that is going to be your next kind of classwork, which will ask you to think about the output when that happens. Okay, I'll come to that soon. Nitin says, basically you mean to say that the barrier acts as a ready queue in OS. I mean, you might be able to view it that way, that if everything is ready, then only start execution. Yeah, you can think about it that way. All right, I'll just give one, okay, where all threads wait before being scheduled. No, actually, it's not exactly that way. The reason I'm saying that it's not exactly that way, as in OS, is that yes, all the threads have to come there into the ready queue, but doesn't mean that all the threads come there at the same time. The way ready queue works is that whenever a thread is taken for execution, it comes to the ready queue. If it is ready, then it is taken for execution. Right? At that time, the other threads may or may not be ready. Whereas in this case, if you have crossed the barrier, that means that everybody is ready at the same time. Then you can call it as a similarity. Okay, so let's move ahead from here. Yeah, I'll give you a small example here. Let's say that I'm executing this instruction, a of thread ID equal to thread ID in parallel by different threads. Okay, and then there is another instruction after that, which is also executed in parallel, that if a of thread ID plus 1 equals 4, then print that I am the third thread. Okay. Now, this particular second line is going to not or may not print it correctly if there is no barrier between instructions. Let's write thread ID equal to thread ID. The second instruction is the if statement. If there is a barrier between the two, all the threads in parallel are going to write to different thread ID locations. A of 0 equal to 0, A of 1 equal to 1, A of 2 equal to 2, like that. All the threads are going to write to this array. Only after all of them have finished execution, I mean, they are running in parallel, so they might run at different times. But if there is a barrier between the two, then no thread is going to execute the if condition until all the threads have completed assignment to A of thread ID. Okay, I'm assuming that thread ID is a local variable. I hope this point is clear. So until we have reached Delhi, nobody is going to start the journey to Kashmir. That is what this means, right? So the if condition is journey to Kashmir. If there is no barrier between the two, let's see what happens. So, okay, let me complete that part first. So, since writing to A of thread ID is over by all the threads, reading of A of thread ID plus 1, assuming that it is within bounds, will always see the previous write by the appropriate thread, right? So thread ID 0, 1, 2, 3, 4, right? So let's assume that these are the threads. Thread ID 3 is going to read A of 4 and it will check that A of 4 should be equal to 4. Correct? Actually, this A of thread ID plus 1 equals 4 is going to get executed by all the threads, right? And only the thread number 3 is going to do the printing of the I am the third thread. So all the threads, so thread 0 is reading the value of thread of A of 1. Thread 1 is reading the value A of 2, and so on. A of 4 is being read by thread number 3, and it will see the value 4 if there is a barrier. However, if there is no barrier, between those two instructions, then there is no guarantee that A of 4 equal to 4 is over before thread 3 checks this condition, right? Because thread 3 and thread 4 are independent. There is no barrier. So thread 3 is executing A of 3 equal to 3, and then it goes ahead and checks A of 4 equals 4 or not. At that time, thread 4 has not even started execution, and therefore this particular statement, printf I am the third thread, may not get printed at all. I hope this point is coming across to you, that because there is no barrier, because there is asynchronous execution between the threads, your output might change. Right? And if there is a barrier, then there is a deterministic output because A of 4 has finished its execution in the first instruction. Okay, when A of 3 reads that value. So the write by thread 4 and read by thread 3 is separated by the barrier. If there is no barrier, then these two writes and reads to A of 4 can happen in parallel, and therefore there is a data race. Okay, I'll also explain more precisely what a data race means, but essentially it means that you can have a non-deterministic behavior. You might see, depending upon the order of execution of threads, you might see different outputs. Okay, if there is any question, feel free to ask. So if you think about these barriers, then there could be more such barriers in the program. So these barriers convert a program into some sort of parallel phases. So you should view the program as starting from, let's say, at the start of main, there is one, think about everybody starting together, right? And then at the end of the execution, everybody is going to finish. Therefore, this whole program is a single phase. You can view it that way. Now, if you put a barrier in between, then that is going to convert your program into two phases. Starting, first instruction in main to the barrier, and the next instruction of the barrier to the last instruction in main, right? So these become two separate phases. Why these parallel phases? I'm casting it in this manner because that means that any instruction in the first phase cannot interfere with any instruction in the second phase, and vice versa. That means that when you want to reason about the programs, you can restrict yourself to a single phase, and that suffices. Okay. Yeah, as Yashpal was asking, is there a way to remove that? Yes, we'll add an async directive, and that will help us remove that barrier, but that will also trigger more possibilities, right? When you have barrier, that is called as, in some sense, barrier separated program. It's called as synchronous execution. So threads start at one place, then they meet at the barrier, then they start again, go parallel, then they meet again, then they go again and meet again, and so on. So this becomes, in some sense, bulk synchronous processing or BSP style of processing. So that is a synchronous execution. They all are syncing with each other after every step or after a few steps. In contrast, if I just let them go, like we said that, okay, we all are going to Kashmir, it doesn't matter how you go. While all of us might go via Delhi, but it's possible that somebody might have reached Kashmir while somebody has not started from Chennai, or somebody might be in transit and so on. So that becomes asynchronous execution. We are not coordinating with each other. Okay. And therefore, the number of such behaviors that parallel threads might have goes on increasing if you have asynchronous processing. With synchronous, the number of behaviors reduce, and therefore the argument about correctness or argument about parallelization might turn out to be easy. Okay, so that becomes your classwork. The code is exactly what it was before, except for this async part that I have added at the end of the first pragma. Right? What you have to think about is that what all outputs are possible beyond what was possible. Definitely, whatever was possible without async, that all is definitely possible with async. Okay, so the number of behaviors is going to be a superset of what was possible without async. Now you have to tell me what are the additional possibilities in this case. And if there are any questions, feel free to ask. Okay, I should probably clarify what that async is doing. That async is removing the barrier between CPU and GPU. Now please think further. Abhishek is saying if we use async, then host can be printed before hello and bye. That's Good observation. Let's see. I'll wait for others to think for that. Dhruv says a single hello will come first, but after that all can come in any order. Okay. Let's see. Himanshu says one or two will always be together, but others can get intermixed. Okay. Sure. Yeah, once again, I'll say that whether you are writing here or not, please make sure that you are trying it out. Okay, so let's discuss this part. When you have async, once again, threads are executing this block in parallel. So, hello by each thread is going to be sequential, but across threads it's going to be parallel. So that part is okay. Printf host, now when the CPU launches this kernel for this pragma, then the CPU is not going to wait because of the async. It will just go ahead and start executing the next instruction. The next instruction is printf, and therefore it is going to print this host on the screen. Right? At this stage, you can say that printing of host by the CPU and the printf's hello byte from the GPU are asynchronously executing, and therefore host can get printed either before hello bytes, in between any of the hello bytes, or at the end of hello bytes. We don't have any control over when that will happen. It depends upon the execution. In fact, most of the times you will see that host gets printed first and then the hello bytes, but that is just probably the implementation aspect. But by default, you cannot guarantee that that will always be the case. Okay. So yes, you guys are right that host can occur before hello, and host can also occur after by, after the last by, and host can also occur anywhere in between. All right. Even if it's a single threads hello and bye, a host can actually get pushed in between that. That is also possible. Okay, so what happens after that? So the kernel is still probably executing, and that printf host has happened. Then after the CPU has completed printing of host, it's not going to wait there. It's going to go ahead because it has completed execution of the printf host. So it will go ahead and see that there is a pragma. So it will try to launch a kernel with 3 threads for the next block. Right now, one kernel is possibly still executing, and another kernel is getting launched by the CPU. Doesn't that mean that hello bytes can get intermixed with 1, 2? Any suggestions on that part? Right. So I think Dhruv has also indicated that all can come in any order. He also says that, and Yashpal also says that it's possible. I'll repeat the question. Isn't it possible that hello bytes might get intermixed with 1 and 2? Suros shouldn't be in the queue in GPU. Okay. So I'm assuming that Suro says possibly not. Okay. So we have these two parties, Yashpal party and Suro party. Let's see who gets more votes. Himanshu says, I still think possibly not. Okay. Pranav says it's possible. Abhishek says it's possible. All right. Pranshu also says that it's possible. Okay. So Suro doesn't have too many votes, but yeah, incidentally, he is correct that he and Himanshu are correct that it's not going to, it's actually going to, what CPU is going to do is to launch this second kernel into the same command queue the way it was doing before. CPU doesn't say go start executing now. CPU just pushes it to the queue, and that is what it will do and go ahead. In this case, it will not go ahead because the second pragma doesn't end with async. So it has to wait at the end of the second block, and if there is an instruction after this printf2, after printf2 and then the closing brace, that command will not get executed by the CPU. But it will not force the GPU from executing that command. It cannot. It will just push it to the same queue, and therefore the GPU driver is going to pull this command by command from the command queue, from the same command queue, and therefore until the first kernel finishes, until these 10 threads finish execution of hello bye, none of the 1 and 2s will get printed. Okay, I hope this part is clear. I know it's a little counterintuitive, but if you think about it logically, that there is a single command queue for the GPU, you will agree that this is the only output possible. Is it possible that host might get printed intermixed with 1 and 2? Any suggestions? The question is it possible that host will get intermixed with 1 and 2? Okay, Just says not possible. Himanshu says no. Yashpal says no. Suro says not possible. So yes, you are right that it is not possible, because until the host gets printed completely, CPU is not even going to look at the second pragma. And therefore, there is only sequential order between host followed by 1 and 2. Okay. And I'll also mention, just for the sake of completeness, that because this question had come up earlier, if you do not have this printf host, and you have the rest of the code exactly how it is shown on the screen right now, all the hello byes are going to precede 1 and 2 still, right? It's not because of the printf host that the first kernel and the second kernel are executed in sequence. No, that printf host has nothing to do with that. It's just that the same command queue gets used, and therefore, even if you have these two pragmas just one after the other, the second pragma, the second kernel is going to get executed only after the effect of the first kernel is over. Okay. All right. So this was a good discussion. Let's move ahead from here. Yeah, with async host may continue in parallel with the device. Can bye precede hello? For the same thread, no. For the other threads, yes. Can host precede the first hello? Yes, that is now possible. Can bye follow the last two? That is not possible. Right? Bye will always be first, and then only any one is going to start. Okay, I was mentioning about data race, but let me formalize that a little bit so that, I mean, in your minds, you might be able to just apply this mechanically. Right? A data race requires 4 conditions to be simultaneously satisfied. These should be satisfied at the same time. First thing is there should be at least 2 threads. Right? If there is a single thread, if there is a sequential execution, then there is no possibility of a data race. Plus, they have to be executing at the same time. If there is one thread which is waiting and another thread which is executing, and then once the execution happens, finishes, then the first thread comes back again. So they are not really executing at the same time, then there is no possibility of a data race. They should be referring to the same memory location. They should be accessing exactly the same memory location. If I have A of thread ID equal to ID, A of thread ID equal to thread ID, then all the threads are accessing different memory locations, and therefore there is no possibility of a data race here. And at least one of them has to be a write. Only if all these 4 conditions are satisfied, then only we can say, then definitely we can say that there is a possibility of a data race, which can cause issues with respect to correctness of your program, and therefore we should avoid data races in almost all the cases. There are some minor cases where data race might still be okay, but almost all cases we should avoid data arrays. So we should write a data arrays free programs. Okay. Just to make sure that we have understood this, I'm just going to give you some examples, and you have to tell me where the data array is or is not, right? And another aspect here is that since all these four conditions must be simultaneously satisfied, that means all these four conditions are necessary for a data array to occur. If I violate any one of them, then I can avoid a data array. I don't need to violate all of them. I just can violate one of them and still I will achieve a data array free program. Okay, which means that, I mean, maybe if I'm running things with multiple threads, if I violate that, that means I'm running things sequentially, at least part of the where data arrays was occurring, and then I guarantee that that part will never have a data arrays. Or maybe I schedule threads such that the two threads which are probably having a data arrays, they will be separated in time. One way of separating them in time is to insert a barrier between them. Right? Then the two parts of the program cannot have the data arrays if the two instructions go into different phases, the way we discussed about the barrier. Or maybe you are not referring to the same memory location, you give individual threads their own their own local memories. That is called as thread privatization. That can also avoid data races, and at least one write should be there. This is a little difficult because this refers to program semantics. But if you are able to avoid that, then also there won't be any data, because everything is going to be done read-only. Every access is going to be read-only access. That doesn't trigger a data race. Okay, so you have to tell me quickly if a data array exists in each of these following statements. What about this? Okay. Okay, you guys are saying no, there is no data arrays, assuming that the thread ID actually refers to different threads, and different threads have different thread IDs. Yes, so then this is not going to trigger any data arrays, right? How about this? Okay, all of you are saying yes. Anybody wants to qualify that?
Because multiple threads will be writing to the same variable sum.
How are you guaranteeing that they are writing to the same variable?
Because it's I mean same memory location, that's why.
Okay, so the reason why
case
sorry, what?
Case 3 same memory location, that's why.
Yeah, so the reason why I asked you to qualify your yes, all of you, not specifically just, is that I never specified that sum is a global variable or a shared variable. Sum could be a local variable, and if that is the case, then there won't be any data. If sum is a local variable, then there won't be any. I have marked that later, but yeah, in general, if sum is a shared variable, global variable, then yes, there will be a data arrays here. How about this?
Sir, one thing, in this sum example, provided sum is a global variable, there is a data arrays. But in the grand scheme of things, if let's say A is an array, I'm taking the sum of elements, right? But in that case, whatever be the operation of summing up numbers, that won't affect my final outcome, right?
That is, what do you mean by that?
So let's say A is a sum array. We are trying to take all the sum of all the numbers. This is essentially that, right?
Right.
So whatever order we do this, add into the sum variable, that won't matter, right?
Okay. No, I think, okay, I'll explain this. So that's a very good point. Thanks for asking that. This particular sum plus equal to A of thread ID doesn't necessarily mean that each instruction is executed atomically. So what is the instruction actually getting converted to? It loads A of thread ID into a register. It loads sum into a register. It adds these two registers and then stores the value back into the sum. Right? So these are at least 4 steps. at the assembly level which get executed. These 4 instructions from different threads, if they are interlinked, then there is no guarantee that you will see the same, exactly the same sum value at the end. If this instruction would have been executed completely by each thread, right, in an atomic way, then what you say is correct. That it doesn't matter in which order we do. This is all commutative and associative, and therefore you will get exactly the same value. That is correct. But this instruction is not atomic. It gets converted into 4 or more assembly instructions, and that is where the problem comes. Right? A simpler example is I++, right, which is similar to this, where we feel that, oh, I++ will happen as a single instruction. It may happen as a single instruction, but depends upon the architecture. Depending upon the architecture, it might actually get converted into load I into a register, increment the register value, and then store that register into the memory location. Right? So all of this, when you intermix across threads, the value that you will see finally will probably be lesser than what you were anticipating. In a similar manner, this sum will be smaller than the actual value that you were expecting. Is that reasonable?
Okay, yeah.
Okay, sure. In case that was not clear, I'll just mention those steps, assembly steps here. Load A of thread ID. Actually, yeah, Josh has written this. Load, then add, and then store, right? So that is good. These can get intermixed. So so think about it this way, that okay, I'll probably take the example of I++. Let's say I equal to 0 initially, and there are just 2 threads, and they both are doing I++. Now that gets converted into load I into register, increment that register, and storing it back into the memory location of I. We expect the value to be 2 at the end of this execution, as happens in sequential execution. Now let's say that both these loads happen together in parallel, so they both load the value of I into their memory, into their separate registers. What is the value of I that gets loaded? 0. Now both of them in parallel execute the increment of the register. Both of them increment their own registers to value 1. After that, both of them end up storing the value 1 to the I's memory location. And exactly the same thing is happening in this sum plus equal to A of thread 8. Multiple threads might read the value, old value of sum, which is probably 0. They add their own A of thread ID, and then write back the value. Now, if this A of thread ID might contain some values like 5, 3, 7, etc., the final value of sum could be one of these that get added, or if some other thread sees some other threads update, maybe it will add some values and so on. Right? So it totally depends upon all possible combinations of these sums that can happen, including the overwrites of the previous thread, because the reading of sum could be may not reflect the updates from the other threads, which is what happens in the sequential order. If there is any confusion, feel free to ask. Okay.
No, this is okay. Yeah.
Okay. Okay. Sure. So the third one was A of thread ID plus 1 equal to thread ID. Does the race happen here? Okay, so I don't see any answers. Rajanne says that no, there won't be any data race. Okay.
For this case, there can be a seg fault.
Sure, yeah, there can be a seg fault if you go beyond the, I mean, if the number of threads is same as the number of memory locations, then the last thread might access something beyond that. Okay, let's assume that there is enough memory available. Yes, that is correct. let's assume that there is enough memory available. What will happen? Okay, so here we are saying that I am writing to a memory location, which is somebody else's thread ID, and I am writing to that memory location, but I am not writing or reading from my memory location, and therefore there is still one-to-one mapping between threads and the memory locations that they are accessing, and therefore there is no data race. How about this? A of B of thread ID equal to 10. Any thoughts? This kind of access is actually called as an irregular access. Maybe in the interest of time, I'll just move ahead. This can trigger an irregular access if you are not having B array to be an array of constants. So if it is coming from input, then you are not clear what is going to be the values, etc. But yeah, in general, this can definitely trigger the data race, because B of thread ID might be the same for two different threads, and therefore A of X might turn out to be the same for two different threads, and they might end up writing to the same memory location, right? So that is one way of looking at it. The second way of looking at it is that, oh, that is okay. If multiple threads are writing to it, it's okay. But the thing is, you are always writing the value 10. So even if multiple threads are writing to the same memory location, they are actually writing the same value. So yes, there is a race, but that race is not really problematic as long as you ensure that one of them is going to succeed, one of them is going to override the other. It's okay, not an issue, and the same logic applies to more than two threads also. Therefore, this is sometimes called as a benign race. It's a race, but it's not harmful, and therefore this is called as a benign race. One last, if there is a shared variable A of thread ID, then there is a data race, and if it's a local variable, then is there a data race or no? Note that it is A of thread ID plus 1. The last one, is there a data race? Okay, Just says no. Abhishek says no. Himanshu says no. Okay, yeah. So there is no data race in the last one. Everybody is writing to a local variable, so there is no problem of accessing something shared with respect to writing. And as far as reading is concerned of A, you can read somebody else's data. Anyway, there is one-to-one mapping. But as far as A is concerned, you don't have to worry because it's only getting read. There is no writing happening with respect to A, so you don't have to worry about that part at all. Okay. All right. So I hope the data race part is clear. Let's come back to our number of gangs, right? So the number of gangs that when we specify, last time we specified 10 and 3, which were constants, but can you specify an arbitrary expression or maybe a variable, right? So yes, it is possible. You can actually pass that as an argument and pass that as a parameter, and then you can run it as a.out10. It will run it with 10 threads. If you run it with 20, it will print hello world by world 20 times and so on. So all of this is possible. The other part that is also going to be possible is that you can invoke function calls and have arbitrary expressions. For example, you can have that n gangs by 2 or some arbitrary expression there. That is also allowed. And this pragma can precede a function, and that function is going to get invoked by all the threads in this parallel part, which means that fun becomes actually the kernel which is executing on the GPU. And this is what we were discussing. Dhruv was asking, can we have arbitrary functions? Yes, as long as this definition of fun is there in your user code, you will be able to run this code directly on the GPU. Okay, and of course you can as well run it on the CPU because that code is available. You have to be careful about what other functions we call from fun. As long as those functions are also defined and the code is available for the GPU, it is all right. Okay, so yeah, you can run it with different threads and you can check for your output. There are certain modes which I would like to highlight. As you start making use of parallel, you might encounter, because if you start with a sequential code, that sequential code might be arbitrarily written. So there are some restrictions on what is possible when you try to parallelize. For example, you cannot have, let's say, some goto which is coming directly inside that parallel block, or there is some goto inside the parallel block which is taking you outside. Right? So there is no branching in or out of it which is allowed. There should not be, I mean, there are multiple clauses which you can give after hash pragma ACC parallel. Those clauses should not be dependent on each other. There should not be any effect of one clause which is making the other clause change its behavior, right? So we have not really looked at too many clauses, but there is another thing which you might want to keep in mind. There is something called an if clause which is possible, as I was mentioning, that you can decide based on certain condition whether to execute that particular piece on the GPU or not, right? So that if, and I'll show you one specific example just after this. Those of you who are aware of OpenMP, there are private and first private clauses supported in case of OpenACC parallel also. Essentially, private means that you can specify which variables are thread local. Like if I have sum plus equal to of thread ID, and I want that sum to be, individual thread should have that sum as a separate variable, then you can just make private sum, and that will create those many copies of sum equal to the number of threads. So each thread will have its own local copy. By default, if there is a global variable or the variable which is defined before the pragma, then by default it is shared across all the threads. So for example, if I have int sum equal to 0 and then there is hash pragma ACC parallel and sum plus equal to of thread ID, whatever be the thread ID, we'll have to define it. Then that by default that sum is going to be shared. Right? First private means that whatever was the value just before the execution of that loop, that value gets copied to individual threads local variable, right? So the first value that you get for the private variable is coming from outside. That is what it means. Right. So the semantics are very similar to OpenMP, but yeah, I mean the first private, unlikely that you will require it at this stage, but private might be required if you want to make some things thread local. Okay. So quickly, what is going to be the output of this code, or whether there will be any output of this code? Can somebody think about it? Okay, Himanshu says no output. Okay. Surya says the CPU will still print hello world. Okay. Rajanya says hello world. Okay. Just says CPU will print hello world. Okay. Pranav says maybe no output. Abhishek says one hello world. Yashpal says only one hello world. Okay. So okay, let's understand this. So if condition gets evaluated definitely, and if the condition is false, then this pragma kind of gets nullified. If the pragma gets nullified, does that mean that there is no output? Well, it doesn't mean that way. It just means that the pragma is as if not there, because this condition is false. But if the pragma is not there, the CPU will still execute it sequentially, and therefore one single hello world on the CPU gets printed, right? Not on the GPU. The hello world gets printed from the CPU. That is the final answer. Not only single hello world, but single hello world from the CPU. Okay. All right. So that kind of completes whatever I wanted to cover about parallel. Although this parallel is rather generic, and it can be used the way we have used for arbitrary computations. Most often it gets used in combination to loop. which we are going to study 2 lectures from now. But nonetheless, parallel has its own semantics, and therefore I thought that you will get introduced to arbitrary things which you can do synchronously, asynchronously with parallel, and therefore we introduced it that way. We will find more uses of it in the context of loops when we combine loop and parallel. So that we'll study later. I'll wait for any questions that you may have. Yeah, once again, I'll say that it's a good idea, it's a good practice if you can try out these programs as well as try out your own combinations. When you try out, you will get some questions that, oh, what happens when I do this, what happens when I move this, what happens if I insert something in between, and so on. So please try out those combinations. And if there is something which you have not understood, feel free to ask me by email or post on Google group. We'll be able to discuss. All right, so I don't see any questions, so we'll stop here and we'll meet tomorrow. And tomorrow we are going to study not the loop part, but the kernel's directive, the magical one that I was talking about, where you just give it a piece of code and compiler will do its magic, right? So that is what we will try to do tomorrow. All right.